got some doggos playing down here. Hello, class. Hope everyone's doing well today. I'm waiting for a few more viewers. Actually, you know what? I'm just going to start. It's their loss. So what we're going to be talking about today is a phenomenon that occurs with it's a phenomenon that occurs when waves superpose. Okay. And so to introduce you to this concept is called the beating of waves, B-E-A-T-I-N-G. So let me write that down actually. So this is AP Physics 1, March 2nd, period 2. And so today we are going to be talking about wave beating. Okay, and wave beating is when two waves of nearly equal frequencies superpose. So just to remind you, wave superposition means two waves are combining to make the total wave, two or more waves. They can superpose constructively, which means that when you combine them, the total wave grows in displacement, or they can superpose destructively, in which case the total wave gets smaller. Okay? Wave beating is when you have two waves that are superposing and they almost have the same frequency, but not quite. So what I'm going to do is I'm going to show you, today's lesson is kind of more, I don't really have to write down a lot, but I have to show you a lot of stuff. So what I'm going to do is I'm going to show you a video from YouTube. And what this video is it's two cars side by side with their emergency flashers on. Okay? Two cars with their emergency flashers on. All right? And so they're blinking. Each car has a... You might have also seen this phenomenon if you are in a turning lane in a car, and one car has its turn signal on, and your car has its turn signal on, and you might notice that the turn signals kind of go together for a while, and then they start to go opposite to each other for a while, and then they go together for a while, and then they go opposite for a while. So let's, you might have noticed this phenomenon before, you might not have. So I'm going to show you what it looks like. Okay. So let me share my screen. Okay, so let's watch this video. Hopefully you can see it. So right now they're opposite. The two emergency flashers are opposite. And now they're in sync. And now they're opposite. Now they're in sync. Now they're in sync again. Now they're opposite again. So maybe you can see that the car on the right had a slightly higher blinking frequency than the car on the left. Okay, and so that's why, you know, if they had the exact same frequency, oops, it's auto-playing the next video, which I don't want it to do. So if the two had the exact same frequency, then they would either always be blinking together, okay, or they would always be blinking opposite, but that the relationship between the two blinkers would never change if they had the exact same frequency. But because they have almost the same frequency, okay, because they have almost the same frequency, they blink together for a little while, and then they blink opposite for a while, and then they blink together for a while, and then they blink opposite for a while. So this is an example of waves beating. So when they're blinking together, that's like constructive interference, and when they're beating opposite, that's like destructive interference. Okay. Another place you might have seen this is if you're doing laps around the track and you're almost going the same speed as someone else, then what you'll notice is that you guys run together for a little while, but then the other person, let's say that you're faster, okay? So you guys are running side by side for a little bit, but then you gradually pull ahead of the other person, and eventually you'll end up on the other side of the track from them so that you're on opposite sides. That's like destructive interference. And then slowly you'll lap them, and then you'll be going around together again for a little bit, but then you'll go opposite, and then you'll be together again, and then you'll be opposites. So this is another example of the beating of waves. Okay, so I'm going to show you what that looks like. All right, so let's share my screen again. And so I have Desmos here. And so I have a graph of displacement versus time for a wave, okay? And so what is the period of this wave? Well, the wave, for a full period, okay, a wave has to go up, do a complete up, and then do a complete down. So one complete up, one complete down, that's a full period. So this amount of time right here. And so hopefully you can see that that's right at 5 seconds because it's halfway between 0 and 10. Okay? So this first wave has a period of 5 seconds. Okay? Now I have a second wave which has a slightly different period. Let's see, the green wave has an up and a down, and it completes its full period right there, which is not in the middle, but it's actually at 6 seconds. So one wave has a period of 5 seconds. The other wave has a period of 6 seconds. Okay, so now I have them both, and I know this is a little bit, it's kind of like overwhelming to look at almost. But what we can see is that the two waves start out, they both have peaks. So they start out together. So they're starting out with constructive interference because both the blue wave and the green wave are going up at the same time. They're going up together. They have peaks that are close to each other. But because the two waves have different periods, different frequencies as well, one of the waves starts to pull away from the other one. And as time goes on, they get further and further apart until right around here, we have destructive interference. Okay? How do I know that this is destructive interference? Well, I know because the green wave is up when the blue wave is down. So what that means is that when we add these two together, we're adding a positive to a negative. So what that means is that we are going to have destructive interference right here because they will cancel each other out. But then they start to go back in sync again until we get to right around 30 seconds where the two waves are together again. Okay? So let's go back to my document camera. So what we noticed is that so in this example, the waves were together at time equals 0. So we had constructive interference at time equals 0 seconds. Okay. The waves were together again at t equals 30 seconds. Okay? The waves were together again at t equals 30 seconds. So what that means, so we would say that the beat period, which is equal to the time between constructive interferences, was 30 seconds. Okay? So it took 30 seconds to go from constructive interference to to the next constructive interference. So we would say that the beat frequency, and remember, frequency is always 1 over the period. So the beat frequency is 1 over the beat period, which would be 1 over 30 hertz. Okay? So that's how it works. Now, one of the things I want to notice, so let's just look at that again just so you can see. So they start out at time 0 in sync, and they're in sync again at 30 seconds. Okay? So the beat period is 30 seconds, so the beat frequency is 1 over 30 hertz. Okay. Now I want to notice, okay, that the period of wave 1 was 5 seconds. Okay. That means that so this is an important equation, so I'm going to box that. That means that the frequency of wave 1 is 1/5 of a hertz. The period of wave 2 was 6 seconds, which means that the frequency of wave 2 was 1/6 of a second. All right. All right. And what I want you to notice is that 1/5, so if I do F1 minus F2, that's going to equal 1/5 minus 1/6, which is 1/30th, which is the beat frequency in this particular example. Okay? See how 1/30th of a hertz was the beat frequency, and 1/30th is also the frequency of one wave minus the frequency of the other wave. So it turns out, and that this is the general rule, the beat frequency is equal to the difference between the two frequencies of each wave. Okay, so this is our main equation for today. Now, because frequency is always positive, we put an absolute value around there because we don't know which frequency is bigger. So it's just the absolute value of the difference. So this is our main equation for today. So your quiz today is going to be using only these two equations. All right. So let's play around with this a little bit more. All right. So the first thing I want to talk about is, or the next thing I want to talk about rather is what happens as the frequencies, or as the periods get closer. Periods or the frequencies. All right. What happens as the periods or the frequencies, etc., get closer together? So let's go back to Desmos and see. All right. So notice how. All right. So let's make them even closer. So now I'm going to make the other one have a period of 5.5 seconds. Okay. And what we can see is that if I make one of them have a period of 5.5 seconds, they're actually now opposites at 30 seconds. And we can see that I have to go all the way, for them to get back in sync again, I have to go all the way over here to like 55 seconds before they're back in sync. Okay? So see how when I make the frequencies closer together, it takes more time for them to come back together again. All right? So let me write that down. So when the periods and or the frequencies get closer, it takes more time for the waves to get in sync again. All right. So the way you want to understand that is going back to the analogy of running around the track. Okay. If you and your buddy are running around the track, if you're just a little bit faster than them, then what you'll notice is that you guys stay together for a longer amount of time, but then you also stay apart for a longer amount of time. So the closer the speeds are, as you and your buddy are running around the track, the more time you're going to spend near each other, but also the more time you're going to spend on opposite sides of the track. All right? So it takes more time for them to get in sync, for you to get back in sync and go all the way around and lap the other person. Okay? So that is an important point. The next question I wanted to talk about is, what does the superposed wave look like? So to answer that, we can go back to Desmos. Okay. And I'm going to change this one to have a frequency of 6 again. Okay. And so remember, when we have two waves, even though these waves have individual identities, we don't see the individual waves. What we see is the sum of the two waves. So see how right here I have f of x plus g of x. So if I get rid of these and then I show f of x plus g of x, it looks like that. So let me zoom out a little bit so you can see what it actually looks like. All right. So they started out in sync. So we start out with a large amplitude. But then as they go out of sync, we get destructive interference. So the amplitude gets smaller. Okay. Then they start to go back in sync. The amplitude gets bigger. Then they go out of sync, and the amplitude gets smaller. Okay. And so it just repeats. Again, we can see what happens if I make the frequencies closer together. You can see that it now took 50 seconds for them to come back in sync again. All right. So when they're in sync, we have constructive interference. So that looks pretty cool. All right. I like the way that looks. So the superposed wave, if we look at the displacement versus time, looks like this. Kind of looks like they're in sync, and then they're out of sync, and then they're in sync. It's really hard to draw. And then they're out of sync, then they're in sync, and so they kind of go in sync and out of sync repeatedly. Okay. All right. The next question I wanted to ask is, what if the waves aren't the same size? Okay. What if the waves aren't the same size? So let's go back to Desmos to look at that. Okay, so I'm going to go back to this one being a frequency, that frequency. So here I have this wave has a amplitude of 1, okay, because I can see it's wiggling between +1 and -1. So that wave has an amplitude of 1. Now, what if I made this wave instead have an amplitude of 2? So now it's twice as large, okay? And then I keep this one at an amplitude of 1. So actually, let's make this one have an amplitude of 3, and this one is going to have an amplitude of 2. Okay, so this wave goes from +3 to -3, and then this wave goes from +2 to -2. All right, so now let's show what the total wave looks like. And hopefully what you can see, actually, you know what, I'm going to make these closer together, is that hopefully what you can see is that because the two waves don't have the same size, they can't completely destructively interfere. So when they had the same size, the amplitude went all the way down to 0. But because they don't have the same size, the amplitude can't go all the way down to 0 because they can't completely cancel each other out. Okay? Now, one of the things I want you to notice is that the maximum amplitude is 5 in this case, which is the sum of the two amplitudes. Okay? 3 plus 2 is 5. The smallest amplitude is about 1. See, here's 1. There's the smallest amplitude, which is the difference of the two. 3 minus 2 is 1. Okay? So basically, if the two waves aren't the same size, you cannot have completely destructive interference. You cannot have completely destructive interference. Okay? And in fact, the maximum amplitude will be the amplitude of the first wave plus the amplitude of the second wave. All right? And the minimum amplitude, which in this case was equal to 3 plus 2. Okay? The minimum amplitude is going to be the amplitude of the first wave minus the amplitude of the second wave, which would be, in this case, 3 minus 2. Okay? So that's how that works if the two waves aren't the same size. So the last question I want to talk about is how do we perceive the beating of sound waves? How do we perceive the beating, like with our senses? Okay. And so what we want to notice here is that the amplitude goes down and it comes back up, and the amplitude goes down and it comes back up, and the amplitude goes down and it comes back up. So and then we want to remember that amplitude is the same thing as volume. Okay? So what we would hear is the volume goes down and it goes up, and it goes down and it goes up, and it goes down and it goes up. So basically, you would hear, we see that the amplitude goes down. I'll say the amplitude fluctuates, meaning that it changes, it fluctuates, it pulses. Okay, it it fluctuates, it pulses regularly. Okay, which means that the volume fluctuates regularly. So basically what you would hear is wow, 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 something like that. Okay? Wow, 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 wow. So that is how we perceive it. Okay? So it's I'm actually going to demonstrate the beating of sound waves for you in the Zoom room. Okay? And so you can actually hear it. I need two sources of sound. I need one source that's playing one frequency and one source that's playing another. And it's just a little bit too complicated if I've got too many windows open right now, so I'm gonna just do it in the Zoom room. I think it'll be easier. Okay, so that is my lesson today. And well, it's not completely my lesson because I'm going to demonstrate the what that sounds like in the Zoom room. Okay, so I will see you there.